Intermediate Algebra for Statistics, Using Exponential Functions to Model Data, Part 3. Lesson Objectives. Find an equation of an exponential model by using data described in words or a table. Make estimates and predictions using an exponential model. Meaning of the base of an exponential function. Summary. If f of t equals a times b to the t power, where a is greater than 0, models a quantity at time t, then the percentage of change is constant. In particular, if a is greater than 1, then the quantity grows exponentially at a rate of b minus 1% in decimal form per unit of time. If b is in between 0 and 1, then the quantity decays exponentially at a rate of 1 minus b% in decimal form per unit of time. Now we'll do some examples of this to illustrate these points. If there is an exponential growth, then the base is 1 plus r, where r is the growth rate. If it's a decay, then it's 1 minus r, where r is the decay rate. So 1 plus r or 1 minus r is the base. If it's a growth, it's going to be bigger than 1. If it's a decay, it will be less than 1, but it will not be negative. The base can't be negative for an exponential function. Let's do some examples. Example 5. A. Is this an exponential growth or a decay? As x gets larger, y increases. So therefore, this is a exponential growth. For this graph, as x increases, y decreases. So this is a exponential decay. B. F of x equals 4 times 5 over 2 to the x power. A is 4, b is 5 over 2, so 5 over 2 is 2.5, which is larger than 1. This is a exponential growth. Next we have y equals 0.3 times 0.8 repeating to the x power. The base is 0.8 repeating, that's less than 1, therefore this is a exponential decay. Number 2, given y equals 1.23 to the x power, identify the growth decay factor, the growth decay rate, and the initial value. Well, the factor just simply means the base. So the base in this case is 1.23. The rate, since this is larger than 1, this is a growth, so the growth rate is this value minus 1, which is 0.23, and normally we write the rate as a percent, so that's 23%. So as x increases by 1, this function increases at a 23% rate. The initial value is the value of a, in this case it's 1. For number 3, we have f of x equals 3 times 4/5 to the x power. 4/5 is the base, it's less than 1, it's 0.8. So this is a decay. So the decay factor is 4/5 or 0.8. The decay rate is 1 minus 0.8, which is 0.2 or 20%. The initial value for this problem is 3. Next we have f of x equals 0.75 times 0.60 to the x power. The factor is the base, which is 0.6. This is a decay. The decay rate is 1 minus 0.6 or 40%, and the initial value is a, which is 0.75. Example 6. The Dow Jones Industrial Average is the measure of the strength of companies on the New York Stock Exchange. Let A equal f of t be the Dow Jones average at t years since 1980. Number 1. Find an equation of f. So when t is 0, we have an average of 839. When t is 2, we have 875. So for this problem, we will pick 2 points and we will find the equation of f. In a future video, we will have data like this, and the graphing calculator will compute the exponential regression model. So first we want to look at the scattergram. Bends upward suggests an exponential function. We're going to use the points 6, 15, 47 and 12, 3169 to model the equation. Again, in a future video, we will allow the graphing calculator to compute the exponential model. So we need to find the values of a and b. That's two variables, so we need two equations. When y is 3169, t is 12, and when y is 1547, t is 6. Divide the two left sides and the two right sides and solve for b. We have 3169 divided by 1547 equals b to the 6. Raise both sides to the 1/6 power, and because this is an even power, we put a plus and a minus. We have b is equal to plus or minus 3169 divided by 1547 raised to the 1/6 power. Using a calculator, that is 1.127. We drop off the negative because b cannot be negative. It will not be an exponential function. So f of t equals a times 1.127 raised to the t power. To find t, we pick a point. I'm going to use 6, 1547. We substitute 6 for t and 1547 for f of t. Next, we divide both sides by 1.127 to the 6th power, which is approximately 755. So the final equation is f of t equals 755 times 1.127 to the t power. Putting this value in the graphing calculator, we see that this exponential curve models the data very well. Number 2, estimate the percent rate of growth of the Dow Jones average. Solution. So this is an exponential growth because the base is bigger than 1. So if we take the base minus 1, we get 0.127 and change that to a percent, and we see that the rate is 12.7%. So in the terms of this problem, the percent of growth for the Dow Jones average is about 12.7% between the years 1980 and 1996. Lesson objective. Example 7. The exponential regression equation for the Dow Jones Industrial Average is R of t equals 776.79 times 1.124 to the t power, where t is the number of years since 1980. Number 1. The Dow Jones averages for more recent years than those in the previous example are shown in the table on the next slide. Calculate the error in using the model R to estimate the Dow Jones averages for the years shown in the table. Solution. Use the model to estimate the average in 1998. We substitute 18 for R and solve. We have 6,369.38. The actual average was 7,908. So if we compute the difference between the estimate and the true value, we have a negative 1,539. The model underestimates because this is a negative number. If we perform the similar calculations for the year 2000, 2002, 2004, and 2006, we see the model didn't do a very good job for 1998 or 2000, but did a very good job for 2002, 2004, not so good, and then it was way off in 2006. Number 2, use a graphing calculator to graph the model of R and the scattergram of the data in the same viewing window. So here we see the model is doing a very good job for this point, but then we have some data values that have a lot more variation. And this happens in the real world, where models sometimes do a very good job and sometimes the estimates are off. Number 3, based on your work in problems 1 and 2, describe how well the function r models this situation. From the table, we see that r underestimates the averages in 1998 and 2000 and overestimates in the years 2002, 2004, and 2006. The model does a good job from 1980 to 1996, but not so well from 1998 to 2006. 4-step modeling process. Define the model and then make estimates and predictions. Number 1, create a scattergram of the data. Decide whether a line or an exponential curve comes close to the points. Number 2, find the equation of your function. It may be linear, it may be exponential. Number 3, verify your equation by checking that the graph comes close to all the data points. Number 4, use your equation of the model to draw conclusions and/or make predictions. Thanks for watching.